Assalamu alaikum. Welcome to this session. In this session, our main agenda is to extend our discussion on the practical side of applying machine learning algorithms. In our previous discussion, we talked about bias, variance, and we talked about regularization. So in this session, we'll be essentially talking about two major things. One is that how to select the model, and for that purpose, we'll have to split our data into pieces. And using those pieces, we'll be talking about cross-validation techniques. So in the nutshell, our fundamental goal is to learn from data. And when we say we have to learn from data, that essentially means that our predictions should be as close to the actual truth as possible. So h theta x is our prediction on the input x. And this prediction is parameterized by theta, which is essentially our weight vector, and y is the ground truth. So we learn parameters by minimizing the training cost. When we say training cost, we need to bring in a loss function. So there could be different possible loss functions. We can use some of the standardized loss functions as we have been using in the context of linear regression and logistic regression, or we might be able to define our own loss function with certain characteristics. So using that loss function, which essentially compares the prediction and the ground truth of the training data, and it computes one consolidate number which represents the cumulative loss if we use theta as the parameter, and that cumulative loss is for all examples in the training data set. So in our notation, M is the number of data items in the training data. So the question is, will the model which we learn uh, perform well on new unseen data? And in our previous discussion, we talked about that there could be two possible problems which may arise. One is underfitting, where the model is highly biased, and the other one is overfitting, where we end up into high variance. And when the model overfits, either underfits or overfits, it is highly likely that it won't be able to perform at an acceptable level on new unseen data. And like keeping that thing in mind, that we are interested in the performance of the model on the new unseen data is extremely important, because that's the kind of reason we have been developing these models in general. And once a model is deployed, it has to face unseen data, and it should be robust enough to perform well on the new unseen data. Okay, this is a quick recall that what did we mean by parameters? So by parameters, we mean we are essentially learning the theta vector. So these are the internal variables of the model. They are learned from the data. And as part of the exercise, we essentially come up with a function, which is a function of x. X is the feature vector, which is parameterized by this vector of parameters, and it yields some prediction. So you know from here that x is something which is not in our control. X is essentially the data, right? So this is the input. So what we can optimize is the vector of parameters. So these are weights which we have already explored in the context of linear and logistic regression. And in the coming days, we'll be talking about the same weights in the context of neural networks. And they're learned by minimizing a loss function, which is our objective function. And theta star is the set of those weights which we have actually learned. So argmin theta over different values of theta will keep on comparing losses against the losses for those particular thetas, and amongst all of them, it will output the weight vector, which leads us to the minimum possible loss in that entire training exercise. And we can use different optimization algorithms, which essentially attempt to satisfy this objective function. So in our case, objective function is the minimization of loss function. And we have already gotten familiar with gradient descent. And gradient descent is an optimization algorithm which helps us to compute the weight vector, which yields to minimum possible loss. Or in other words, we are approximating the global minima over here in terms of loss. Okay, the second type of parameters are variables which are in the game. We have been talking about them informally. So those are called hyperparameters. By hyperparameters, we mean that these are external configuration choices, and they are decided before the training process starts. So for example, what could be the learning rate? The learning rate is something which is fixed during the training exercise, right? When the training process starts, alpha is already fixed. So we don't learn alpha during the training process, but as a machine learning engineer, it's our task to choose an appropriate value of alpha before the training process starts. But the question here is that we don't know the ideal value of alpha in all cases. Similarly, another hyperparameter could be the regularization coefficient. So what should be the strength of regularization term lambda before we have to decide this before the training process, right? We can't learn the value of lambda, the ideal value of lambda during the training process. So this is another example of hyperparameters. Okay, what kind of model we need to fit? So what should be the degree of the polynomial which we have to go for, right? So will a simple line suffice to capture the underlying relationship? So for example, should we just go for theta naught plus theta 1x? Or we need to go for some polynomial of relatively higher degree. So for example, or we need to go for theta naught plus theta 1. Apologies for the poor handwriting. Plus theta 2 x square. And there could be so many other possible candidates like theta naught plus theta 1x plus theta 2x square plus theta 3x cube and so on. So this degree of polynomial has to be decided before the training process starts because we don't learn the hyperparameters during the training exercise. So these hyperparameters primarily control the model complexity and the learning behavior. So for example, in our previous discussions, we did talk about the role of alpha. So if we choose a larger value of alpha, what will be the kind of impact which it may have? So having a reasonably large value of alpha might be unable to make the algorithm converge to the global minima in terms of loss function, right? And at the same time, choosing a very small value of alpha might be making it very slow because it will start taking very tiny steps towards the towards the optimal point. Same way, if we choose a very high degree of polynomial, we might be landing into something which we termed as overfitting in our previous class. And having a very low degree of polynomial again will take us to the other extreme, which is underfitting. So how they're chosen, they are not learned directly from the training data during the training exercise. So instead, we use different validation techniques, which we'll be studying today. Particularly, we'll be talking about cross-validation in a while. So we use validation techniques to land onto a reasonably good estimate of these hyperparameters. So yeah, the summary of parameters and hyperparameters. Parameters fit the training data, and hyperparameters help in controlling the generalization. When we say generalization, they actually uh, help us in balancing the trade-off between bias and variance. So because we know from our previous discussions that bias and variance are two major contributors in the error. So if bias is very high or variance is very high, they lead to underfitting and overfitting respectively. So we have to create a balance which is something in between. Right? So by that, I mean, let me try to draw a curve to explain this part over here. So if I try to plot the error over here, so this is the kind of thing that we can see over here. The error is gradually decreasing as we go along. So more specifically, we are like in the component which we are trying to draw over here is the component which is making up which is primarily composed of this first component of error, which is bias. Let's try to draw the other component as well. So if we try to draw the variance, so at the start it might be very low variance and it might be looking somewhat like this. So if we try to add these two curves, because they will be cumulatively making up the error. So if we add them together, so approximately we'll be having somewhat like this kind of curve. So on the extremes of this blue curve, we have either high bias or high variance. And that's why cumulative error is also high. On the y-axis, we have the error. So there's a point somewhere over here where we can go for a good compromise. Over here, the cumulative effect of bias and variance is approximately minimum, right? But we can see from the green and red curves that these are not the individual minimum points for bias and variance. But there's a trade-off, right? So if we try to minimize bias further, we will have to increase variance and vice versa. So by bias and variance trade-off, we mean that we have to go for a point where we can come up with a reasonably good balance between bias and variance, and they cumulatively contribute to the error. So the purpose why are we interested in hyperparameters? Because they help us to balance that trade-off between bias and variance, or in general, in other words, they generalize the model to work reasonably well on the data which has not been directly used for training purposes. Okay, so for that purpose, we divide data into three different sets. The first set is called training set. We'll be using the notation strain in our discussion. The second set, which is very important, is called cross-validation set or validation set, or from the practical perspective, people call it development set as well. So we'll be notating it as SDEP. The third subset would be test set. We'll be notating it as S-test. So their primary role is that we are familiar with the primary role of training set and test set in our initial exercises of logistic regression and linear regression. So when we say training set, that means that this is the set of data points which has to essentially serve as the guide to learn the parameters. So theta is optimal theta is approximated using training set. And then we directly use S-test to figure out that whether the learned model is good enough or not on some unseen data. Right. So for like some raw purposes, you might have seen at the start of the course, so you might have done these kind of exercises that we use the whole data set as the training set, and then we use the whole data set as the test set. That essentially means that we are trying to measure the performance or robustness of the model on the same data which was fed in for the training purposes. So, but now we are categorizing that entire data into three different isolated non-overlapping parts. One is training set, other one is dev set, and third one is test set. So there is like there are different like conventions, there are different practices that how the entire data should be split into pieces. So one possible way is that we divide it in this way, that training set is 60% of the entire data, 20% goes in dev, and 20% goes in test. Now, you can see from these figures that the training set in its total quantity has to dominate the remaining two subsets, but there's a catch over here. If you have a reasonably large data set, then this could be a like acceptable kind of split. But if you are already like struggling in terms of availability of data in a particular problem domain, if you have if you don't have like sufficient amount of data, then just like using 60% of data will further shrink that data, and we might not be able to learn the underlying theme of the data. So that might not be a good choice, but like there could be some other alternate choices. It's essentially the choice which machine learning engineers make. So you can be going for 80%, 10%, and 10% respectively. Or there could be a situation where you are really, really interested in the training exercise. So you want to use as much as possible amount of data for the training purposes. So you might be going somewhat like some extreme kind of split as well, like 90% goes in training, 5% goes in dev, and 5% goes in test. So these are the kind of scenarios where people are really interested in training the model in such a way that bulk of stuff, like if it's an attempt that almost all possible situations should be fed in the training exercise, because even a small improvement in the performance matters a lot for your purposes. So for example, in the context of digital marketing or advertisement, people are like interested in improving the performance of the model even like by tiny margins. So in those kind of situations, pushing in bulk of data in the training in the training exercise might be making sense. Okay, so what we know is that our task is to learn the parameters. And for that purpose, we use our objective function. We want to optimize the objective function, and we learn theta star by optimizing the objective function. So over here, you can see that the main thing which we have to be explicitly careful about is that our component, our subset, which we call strain, will be used to fit the model to learn the parameters. And in order to evaluate the model, we'll be using dev set, which is the validation set, right? What does that mean? That means that as we have started building up a model, we have to learn parameters, but parameters will be learned using the data in that entire training exercise using gradient descent in our context. But who will tell us that what kind of hyperparameters are going to be the ideal ones? So we'll have to do different experiments. So we'll run one experiment for each value of those hyperparameters. So we will create a pool of candidate values of hyperparameters, and for each of those values, we'll be running that entire complete Greenwala part, which is our training exercise. So the blue part is focused on the dev set, development set. So whatever you have learned using your fundamental training data, you will validate it using this blue wala part. What does this mean? This blue wala part is actually wrapping the green wala part. So for each iteration in the blue wala part, you will be running the green wala part. What does that mean? So for each iteration, we mean that for each value of the hyperparameter, you will train the model and see how good is it on dev set. Note it down. For the next value of that hyperparameter, retrain Greenwala part, come up with theta star, and evaluate it on the dev set and see that how good or bad is this new uh, performance value against the previous value of hyperparameter. So for all hyperparameters, we'll be doing this exercise as an ML engineer. And then we will settle down for the acceptable values or the optimal values, approximately optimal values of hyperparameters where our model works reasonably well. Now you can see that the evaluation part, the blue wala part जो text लिखी हुई है, this is essentially a search process for the optimal value of the hyperparameters. But the search is pretty expensive. Within that search exercise, we are doing that entire training exercise for in every iteration. And we are not using the training data over here for the evaluation purpose. This is an important thing which you have to keep in mind, and we'll keep on discussing as we go along. So in the nutshell, we have been given the training data, which is in the form of the feature matrix and the ground truth. We train the model. The model is output as part of that training exercise, which is essentially a learned function parameterized by theta. And then we bring in validation set. Using the validation set, we choose lambda lambda is essentially a representation of a hyperparameter. And then we repeat this exercise. So this repeating exercise essentially means that we are these two parts, the blue wala part and the green wala part. And so green wala part is essentially happening over here, and the blue wala part is happening over here, and we are iterating over this entire process, right? So we'll keep on repeating this cycle until we as an ML engineer decide that we are now fine. We have learned something. We have approximated the reasonably acceptable value of hyperparameters. So what could be the hyperparameters? So it's not necessarily that we are just looking for the ideal value of the regularization strength coefficient. We might be looking for the ideal value of alpha, which is our learning rate. We might be figuring out that how many iterations are really ideal for the training exercise. And we might be looking at that what should be the degree of the polynomial which we are learning as our target model. If you have a look at this visualization, so on one side we have error, the other side is number of iterations, which we have plotted over here. And you can see that the training error is high at the start. So what is training error? This is the error which our loss function is computing and it's trying to minimize. And as we keep on increasing the number of iterations, so our model actually starts getting settled in a good way. And you can see that there is a continuous decline in terms of the training error. But in this entire exercise of searching the optimal values of the hyperparameters, we are also computing the performance of the model. We are evaluating the model on our SDEV. So SDEV के ऊपर जो आपकी performance है, that is validation error, that is the green curve. So that's also high at the start. So it like makes sense that let's keep on increasing the number of iterations because both of the errors are high. So that kind of trend is pretty fine up till roughly this point. But as we cross this dotted barrier, there is a continuous decline in the training error, but the validation error starts increasing. So validation error is being computed on SDEV. And keep in mind that SDEV is unseen. It's unseen for the model because the model has been trained by strain, has been trained on strain. And SDEV is being used to validate the model. So as the error starts increasing over here, that means that now the model is going for something which we in our previous class we called memorization. And memorization means that model is oversettling or oversetting itself for the training data, and that there is the kind of situation we call overfitting. So we are we are landing into the increase in the variance. So that means that this side is actually now taking us to overfitting. So, and what is the opposite extreme where the bias is high? So the other side is underfitting. Okay. So in this entire exercise, we have to stop the model somewhere around this point where we see that this is the good balance between the training error and validation error. And if we keep on running the training process beyond this point for more iterations, that is going to give us a clue that training error is getting reduced. But if we look at the validation error, that actually starts increasing. So that is the critical role which we are looking for from SDEV, and that helps the model to stop at a point. So we are looking for a good balance between these two extremes. So our model selection exercise has the goal to learn a model that generalizes well on unseen data. So we have already discussed that there are so many candidate models, for example, different degrees of polynomials, different regularization parameters within them, regularization parameters, learning rate, and other hyperparameters as well. So it like from nature of because we're talking about models in general. So when we switch to like different models, like for example KNN, so other hyperparameters come into play. That what is the ideal value of K, and so the naive idea is that pick a model with the lowest training error, but we have already discussed that that is not a good choice. That leads to overfitting, and that might be performing poorly on the new data. So for that purpose, we need to have these three sets. We have already talked about that splitting the data into three subsets is a critical exercise as an ML engineer. So why this works? Because validation set primarily simulates unseen data during the training exercise. From our entire training pool, strain is the subset which is being used to learn the parameters, and sdev is the subset which is simulating the unseen data, because our model has to be eventually shipped, deployed in the real settings, and it will have to face unseen data. So that is the kind of exercise which we are doing during the training process and during the model selection process, that it should be evaluated in-house on the unseen data. So the idea of this is just an analogy. The training set is the set which is being used to learn. Validation set is where you are assessing the performance of the learner, right? The learner could be you, right? So if you learned a concept on some data, you are being posed different questions using the validation set to assess your performance. Like you learn from a book, that is training. You solve practice problems, that is validation. Then you sit in the exam, that is your test set. So key principle is that never evaluate yourself on what you have memorized. So if you have, just imagine that you were trained from some content, you were trained on a content from a book, and you use the same content for your own internal evaluation, and you see that I'm good enough with this book. But as you sit in the exam, you have to face unseen questions. So that's where the performance of learner will surprisingly will give us like big surprises, and actually will lead us to some unsatisfactory results. Okay, so let's have a look on some possible model choices. So for example, we have a pool of models with different degrees of polynomials. So 1, 2, 3, 4, and 5 are the candidate degrees. So what we'll do is that we'll train each model on training set strain. We'll compute the validation error using sdev for each of those degrees. And in the entire exercise, once we have the validation error for all of those degrees, we'll choose the degree which gives us the lowest cross validation error or lowest validation error. And similar kind of exercise can happen with other hyperparameters. For example, we have different candidate values of lambda, and we'll do the same exercise which we did for degree of polynomials while hyperparameters. For all hyperparameters, we'll be just repeating this exercise. So yeah, so these this exercise has been laid down over here as an algorithm, and eventually lambda star represents the hyperparameter which has been selected as as a representative of the ideal model, which gives us lowest possible error on the on sdev. Once done, this is the extremely important part. What should we do next? Now that appears that we are ready, that our model is now pretty much done. We have selected a model which, when we say we have selected a model, that means that we have chosen hyperparameters which are now good enough to settle with that set, and expectation is that that will work well on unseen data. So हमने अपने ड्यूरिंग दिस एंटायर प्रोसेस ऑफ मॉडल सिलेक्शन हमने अपने ट्रेनिंग डेटा को इस तरह कॉम्प्रोमाइज किया हुआ था कि हम उसमें एक एस ट्रेन था, एक एस डेव था. So SDEV was part of the data, but was not being explicitly used for the training purposes because we needed that for internal evaluation. Now, once we have settled for the ideal values of hyperparameters, so we can use SDEV to further optimize our model, and we retrain the model on the union of strain and SDEV, which means this is a combined set of examples coming from training as well as development sets. And we use both of them together to train the model. When we are increasing the data, now chances are that model will be more robust. Why we are using SDEV now for training? Because we don't need SDEV anymore. Why? Because we have already selected lambda star or the ideal pool of hyperparameters for our model. So we just use lambda star, which is the representative of the selected hyperparameters, and we use this complete data for training purposes. Once done, now the model is pretty much in a decent shape and can be deployed. Okay, now once the model has been finalized, it has been retrained on the union of those two subsets, and we have selected the model, we have selected the ideal hyperparameters. And as part of when we say retrain, that means we have also selected the ideal pool of weight vectors, theta. So we can do is testing on the completely unseen data which has not been used so far, which is our S test. And this is our final evaluation. So it should not be used more than once. If you use it repeatedly, it becomes part of training. And again, some bias might be induced in our performance estimates. So now over here, a quick comment on the role of testing data. So in our research exercises, in our course exercises, this is an important step because we have to advocate the performance of our model for a particular problem to the external audience. We need to pitch our model कि ये एक particular situation में अच्छा काम करता है on the unseen data. So over here, the role of S-test is pretty obvious and important. But for practical purposes, if you have a client, the client might not have really released an explicit S-test for you. So once you are done with the complete process of retraining that selected model on the complete data, you can just ship it, and the testing exercise might be actually coming in from the real use in the industry or in whatever situation you are into. Okay, now this is time for ICPs. So pause the video, try to figure out what is in the questions. For all ICPs, I would strongly urge you to pause the videos, figure out the answers, give yourself a little bit more of time. This will be a good reflection on what kind of stuff you have understood from the recent discussion. And once done, then you can move forward and the answer will also pop up on the screen. So what if we use strain in place of SDEV? So if you pause the video, you might have figured out this is what we've recently discussed, that model will try to memorize strain, and that will lead us to the problem of overfitting. Because we are essentially evaluating the model on the same data which was used for training purposes. So the unseen data is pretty much upset. Another ICP, if we use strain in place of SDEV, which model will be selected in terms of degree of polynomial? So can you guess that if you just use if you use like the same data for both purposes, for validation as well as training purposes, what is the kind of degree of polynomial which would be selected? If you pause the video, you might have landed onto the answer that it is going to be the highest degree of polynomial which is possible in that entire search process. And why is that the case? In our previous class, we saw that as we keep on increasing degree of polynomial, the model converges to something, model lands into an overfitting value situation. It over memorizes, it overfits itself with the data points which are part of the training set. And that might be leading into a complex curve, but that might not be true, capturing the underlying phenomena in a true spirit. Another ICP, what if we use SDEV in place of S-test? So again, if you pause the video, you might have landed onto this answer that this is not a good evaluation of the model because that model has already been optimized for SDEV. we have selected the hyperparameters keeping SDEV in consideration. So we know that during the training process, we have finalized the model where the performance on SDEV was minimum. So using SDEV again for testing purposes won't give us any additional clue about the model performance on unseen data. So what is the main role of SDEV in the entire pipeline? It helps to select an acceptable model that can be shipped for deployment. So the smaller value, if we select a smaller value of the hyperparameter lambda, that leads us to overfitting. The larger value will take us to underfitting. So cross-validation actually helps us to create a good balance between those extreme possible values of hyperparameters. And the best model which we select as part of this exercise of cross-validation is where we minimize the validation error on SDEV. Okay, we are now going to talk about two validation techniques, which are like very commonly used in practice as well. So the problem at hand is that if we have been given the whole data set, our first task, which we have seen in our previous slides, is to split the data into three subsets. So how to split the data? So if I just split it in a random way or in a deterministic way, by deterministic way, I mean that, for example, if I have been given this whole data and I just make a cut that this 60% goes in strain. So let's say this 60% goes in strain. And then I say, okay, let's say this next 20% goes in SDEV. And the next 20% goes in test. So is it going to be a really good split? Is it a good representation of the underlying phenomena? We don't know, right? So it's a reasonably large data. Things might be generalizable, but there could be a situation that by chance we have induced some bias over here, that one type of problem is over here and other type of stuff is here. And so things might not be like these subsets might not be representing a comparable underlying distribution, right? So single split is not a stable choice, even if we come up with a different strategy of splitting the of making those cuts. So we just wanted to get rid of this single split values, and we want to make it more generalizable. So what we do is that in this is a cross-validation technique, which is called k-fold cross-validation techniques, k-fold cross-validation technique. So the idea is that split data into k-folds, k-partitions, train your learner on k-1 folds, and validate on remaining fold, right? So out of k folds, we are using k-1 for the training purposes, and one is being used for the evaluation purposes. This one step is just pretty much a copy of what we have already seen, that we fix the cut parts, that this is the training part and this is the validation part. But the one difference over here is that we can see that when we say k-1 folds, that is a reasonably larger amount of data as compared to just one fold. The critical part comes over here, that we repeat this exercise for all folds. What does that mean? That means that every fold eventually serves as a validation set. And across those different exercises, we average the validation error as we go along. So this gives us more reliable estimate of performance as compared to a single split. So let's try to have a look on the same thing visually. So we have been given the whole training data at the start. We divide this into different folds. For example, if you look over here on this exercise, we are training the data into 5 folds: fold 1, fold 2, fold 3, fold 4, fold 5. Each fold is a non-overlapping, approximately equal sized partition of the given fold training data. So that training data has been divided into, so if we had m items over here in the training data, when we are dividing it over 5 different partitions, so approximately each partition has size M over 5. And in the first iteration of our k-fold cross-validation technique, what we do is that we pick the first fold, we pick the first partition as our SDEV. So this first one is going to serve as SDEV. So test is not really a good term over here. SDEV, this is essentially SDEV. And the remaining four are serving as strain. So this remaining part is strain in our first iteration. So what we do is that we run our entire exercise, we train the model, and we evaluate its performance on SDEV, and it gives us a performance measure for iteration where we get a number that how good or bad was it. Then what we do is that we go for iteration 2, and this time, but the major change is that we bring the previous SDEV back into train. So that part, so the union of all these four folds, the blue folds, they become a part of strain, and we have one SDEV over here. So the second fold becomes SDEV. We run the exercise, we compute another performance measure. We repeat this exercise. So you can see over here that each fold is serving as SDEV at some time. And as a result, depending on how many iterations we perform, because that number of iterations are essentially dependent on the value of k. So this is a 5-fold validation in this example. So we got 5 different performance measures, and we aggregate those performances by simply averaging them. And that gives us a very good estimate of the robustness of the model, that how good or bad is this entire training exercise while using k-fold cross-validation. So this is more stable and more robust, more reliable as compared to just coming up with one split and come up with a measure and claim that my model is performing this much on this particular split. So over here, our split is the bias within that split exercise has been pretty much eliminated. Okay. So another cross-validation technique is called leave one out, LOO. So the idea is that use almost all data points for training and test on just one example at a time. So this is how the procedure works. If you've been given M training examples, we run this exercise M time. We use M minus 1 examples out of M examples as our S train. So S train is now reasonably large. It's approximately same as the original data set, except one ith point has been put out. So in the first iteration of the loop, I is 1, so example number 1 will be left out. And that left out example is used for the evaluation purpose. And then when I is 2, we put the previous example back and pick the second example and test it on that. So this entire evaluation process would have happened M times because loop is running M times, and each example is at some point serving as an evaluation example. So we average out the error, and that is called leave one out error. So that is our final aggregated performance, which we get as a result. So if we have a look on this from the visual perspective, so we had a complete data of M examples. We pick the first example as our SDEV, and the remaining examples are fed in as training purposes. And we repeat this process for every example. So M times this entire process is repeated, and one aggregated performance is eventually reported. So this leave one out approach maximizes training data using in each run. When will it be more useful? So for example, if we are already running in shortage of data, for a particular problem, if we don't have like sufficient amount of training data, then cutting it into train and dev sets is going to be a somewhat compromise, and we will be further shrinking in terms of our training data. So in those kind of situations, leave one out is going to be an attractive choice because it does not reduce the amount of your available data much. It just takes one example out at one time. So, and each part eventually independently gets a chance to act as the validation data parts. So low bias estimates of generalization error are expected if we apply leave one out. Computationally, it's going to be expensive because if our this entire exercise is pretty expensive because if M is reasonably large, so we have to train M models, right? So this has to be M, this variable is N. So another ICP, what is the difference between K-fold and leave one out cross-validation approaches? So if you pause the video, you might have figured out that leave one out approach is a special case of K-fold, where K is equal to M. K was the number of partitions. So over here, we are dividing our entire set into M partitions because each individual item is going to serve as a partition. So this is a special case of uh, K-fold cross-validation. So this is a detailed comparison between leave one out and cross-validation technique. And I can leave it for you. These are the kind of things which we have already discussed, but you can study this table as a self-study table just to summarize things and the kind of small computations we have done on the right-hand side, that how many examples are being fed in the training exercise and how many are left for the validation purposes in the context of K-fold validation. Just verify them and try to have a good intuition behind them. These are the kind of validation techniques which will always stay with you in your entire machine learning journey, much beyond the course as well. So in this session, what we have learned is that cross-validation helps choose good hyperparameters, and choosing good hyperparameters is extremely important to build robust models. Training error is not reliable alone, can result in overfitting. So we use validation set to estimate generalization performance. Or in other words, when we say generalization performance, that means that we are talking about the performance on unseen data because our SDEV simulates the unseen data. K-fold cross-validation provides reliable estimates, and leave one out cross-validation is a special case of cross-validation. That's it for today. Thank you very much.